Welcome back to Decentralized Application Development Crashcasts. I'm Sheila, and if you're enjoying our show, please take a moment to rate us on your favorite podcast platform. It really helps us reach more developers like you. Today we're diving into Chapter 3 of Season 2, where we'll be exploring feeds and data blocks in the Hypercore protocol. Victor, are you ready to feed our listeners some juicy data?
Absolutely, Sheila. I'm excited to break down these core concepts of Hypercore. Before we dive in, let's challenge our listeners with a quick quiz. What do you have for them today?
All right, listeners. Here's your quiz question. In a Hypercore feed, what's the maximum number of data blocks it can contain? Is it A, 1 million, B, 1 billion, C, unlimited, or D, depends on available storage? Take a moment to think about it, and we'll reveal the answer at the end of the episode.
That's an intriguing question, Sheila. It really makes you think about the scalability of Hypercore, doesn't it? I'm curious to see how many of our listeners have encountered feed size limitations in their projects. But let's not give away any hints just yet.
Agreed, Victor. Now, before we dig into feeds and data blocks, could you give us a quick refresher on what Hypercore is?
Certainly. Hypercore is a secure, distributed, append-only log. It's a fundamental building block in the hole-punch ecosystem, providing a way to store and synchronize data in a peer-to-peer network. The key here is append-only, meaning you can only add new data to the end of the log, never modifying or deleting existing data.
Thanks for that recap. Now, let's focus on feeds. What exactly is a feed in the context of Hypercore?
Great question. A feed in Hypercore is essentially a sequence of data blocks. You can think of it like a digital diary where each entry is a data block. Just like you can only add new pages to a diary, you can only append new blocks to a Hypercore feed.
That's a helpful analogy. So, if I understand correctly, each feed is a separate diary of data. But what exactly are these data blocks? How are they structured?
Exactly right, Sheila. Data blocks are the individual units of data stored in a feed. Each block can contain any type of data. It could be text, JSON, which is a common format for storing structured data, binary data, or anything else. The important thing is that each block is immutable once it's added to the feed.
Immutable, meaning it can't be changed after it's added, right? But how does Hypercore ensure the integrity of these blocks?
That's where the magic of cryptography comes in. Each block is cryptographically linked to the previous blocks in the feed. This creates a chain of trust, similar to a blockchain. When you add a new block, Hypercore generates a signature for it based on its content and the previous blocks. This way, any tampering with the data would be immediately detectable.
Fascinating. It sounds like this structure provides both append-only functionality and data integrity. But I'm curious, are there any size limitations for individual data blocks?
Good question. While there's no hard limit on block size, it's generally recommended to keep blocks relatively small for efficient network transfer and storage. Large blocks can slow down synchronization and make partial replication more difficult. A common practice is to keep blocks under a few megabytes, but the exact size can depend on your specific use case.
That makes sense. Now, I've heard the term sparse replication mentioned in relation to Hypercore. How does that relate to feeds and data blocks?
Sparse replication is one of the cool features of Hypercore. It means that peers don't need to download the entire feed to start using it. They can selectively download only the blocks they need. This is possible because each block is independently verifiable thanks to the cryptographic structure of the feed. Think of it like being able to read specific pages of a book without having to download the entire book first.
That sounds really efficient for distributed systems. Are there any common pitfalls or misunderstandings developers should be aware of when working with feeds and data blocks?
Definitely. One common misunderstanding is thinking you can modify or delete data once it's in a feed. Remember, it's append-only. If you need to update data, you actually append a new block with the updated information. Another pitfall is not considering the implications of feed size growth over time. While feeds can grow quite large, it's important to have a strategy for managing long-term growth in your application.
Those are great points, Victor. Before we wrap up, could you share a best practice or tip for working with Hypercore feeds and data blocks?
Absolutely. One key tip is to design your data structure carefully. Since you can't modify existing blocks, it's crucial to think about how your data might evolve over time. Consider using versioning in your data blocks or implementing a schema that allows for future extensions without breaking backwards compatibility.
That's excellent advice, Victor. Now, I think it's time to reveal the answer to our quiz question. The maximum number of data blocks a Hypercore feed can contain is C. Unlimited. Hypercore feeds can theoretically grow indefinitely, limited only by available storage.
Exactly right, Sheila. While practical limitations like storage capacity exist, there's no inherent limit in the Hypercore protocol itself. This allows for incredibly scalable and long-lived data structures.
Thank you, Victor, for this enlightening discussion on feeds and data blocks in Hypercore. Let's take a moment to sum up what we've learned today. Listeners, here are the key takeaways.
Great idea, Sheila. Here's a summary of what we've covered. Point 1. Feeds are append-only sequences of data blocks. Point 2. Data blocks are immutable and cryptographically linked. Point 3. Sparse replication allows for efficient partial downloads. Sure, careful data design is crucial due to the append-only nature. 5. Feeds can grow indefinitely, limited only by storage capacity.
Listeners, we hope you found this episode informative. If you did, please visit crashcasts.com, join our Discord community, or support us on Patreon. Your engagement helps us continue producing this content. Until next time, keep coding and stay decentralized.